So maybe I will just start with a very high-level quick question. So during all those talks today, or most of them, we saw a lot of figures showing what happens when you scale data and scale parameters. So my first question is, do you think SSL now is at a stage where most of the details have been figured out and we just need to scale in terms of data and parameters? And if not, what do you think is the main bottleneck? So, whoever wants to start.
The answer is no. I don't think we have a perfect recipe yet, in the sense that the stuff that seems to work the best or the most efficiently for images and video to train JEPAs. So first of all, it's got to be a joint embedding method, not a method that works by reconstruction. I can make that point really clear. I'm sure a lot of people here disagree. I have a lot of colleagues who disagree, but like, this is something I feel extremely strongly about. And we have lots of empirical evidence for that. But so it's easy to train by reconstruction. It's not that easy to train joint embedding because it can collapse. So the question is, what is the best anti-collapse method, which is why I talked about to some extent. And as I said, contrastive methods don't scale very well with dimension. So I'm a little skeptic about them. The EMA type distillation methods work well, but EMA is pain in the ass. And I think it comes with a lot of limitations. I'm not so worried about the fact that we don't understand why they work, although probably we should be a little worried about it. Conceptually, I think the Infomax method have all the desirable properties, but we haven't really gone to like a completely perfect recipe that we can just turn the crank on and give to people and apply to everything yet. So no, we haven't figured out a good recipe. It's not just a matter of scaling.
Yeah, and to add something, I don't think we have actually any evidence that just scaling the data work. Like if you look at any work trying to scale, then there is a huge data curation effort, like automatic data curation based on labels. So you kind of add back also a bit of supervision this way. So I don't think we are at the stage where we can just throw more data to the system and hope that it works better.
Yeah, my answer is obviously no. There are two things. I think one is about architecture. Another one is about the data. So the architecture is really the mechanism. How do we learn distribution of the data efficiently? I think one of the fundamental, as I said in my talk, right, that we really need to learn from the nature again, right? Our brain, the architecture is different from the current, the large model, the ones even we scale, and we have to optimize all the parameters simultaneously. I mean, if we want to get away from the BP type, and we have to explore completely new architectures, allow us to learn the data distribution, some parallel, highly distributed approach, just like a cortex. We have to learn that. And from the autonomy of the brain, I mean, something for that, so that it will enable optimization mechanism, not BP type. Second is about what to contain. Such architecture has to learn what distribution. I think as obviously computer vision, we have to learn the 3D world or 3.5D, right? Space and time. Obviously, we're learning all the distribution just from 2D images. I mean, as some of our work that I think Drew Lindsay has said that if you learn this distribution, if you learn the perfect distribution of natural images, still you cannot understand 3D, spatial relationships, and so on and so forth. So our brain has two, right and left, right? We have two eyes. We self-train ourselves with our left and right eyes and capture 3D information. I think there's a reason why I have two eyes, because we live in the 3.5D world, right? 4-dimensional world. And taking snapshots of 3D and you have to learn from the right kind of data that contains the right information. And so we can learn the right distribution, the 2.5D distributions correctly. the physical laws and so on and so forth, the geometry and so on, right? So we cannot imagine we can scale up the ImageNet, the internet scale data. We can learn a physical world. Even from videos, I'm skeptical. The reason why I have two eyes, we have two eyes to learn, right? Maybe make the learning is easier. I'm not saying it's impossible to learn, all right? 3D information from molecular videos, but that's just mathematically computation much harder problem, right? There is a reason I think nature chose to have two eyes, right? So probably it's much easier setting for self-supervision and so on and so forth, you know.
Yeah, I mean, I've learned not to have any strong opinion on anything in deep learning, so I'll keep with that tradition. Yeah, I don't know. I mean, in particular, I guess I'm making peripheral comment, but almost every time I said, a model is not going to be able to learn X or Y, from vision, I was proven wrong. And I think the last example is really Dino, where, I've seen, so I don't know how much, massaging there is and finessing there is with the demos, but hopefully there are smarter people than I am around here that have a better intuition, but I still don't understand why those models are able to learn figure ground, for instance, simply from data augmentation. That seems like, or even depth queues, which would presumably seem to require some sort of video data or some sort of motion information or change in perspective. And so I don't know. Bottom line is that I don't know. I mean, certainly, just to respond to his points, as a neuroscientist, I wish I could say, I think the brain will be the answer. And certainly, the point we've tried to make is that perhaps we will need to rethink the data diet and the objective functions if we want those models to learn more human-like representations. But I'm not sure this matters for engineers at Meta, or I'm personally not sure that the brain will give us a path forward for AI. I'm actually quite convinced that the constraints on brains and machines are quite different in that way. Depending on the goal, the brain may or may not be a useful guide.
Yeah, so do we have the right algorithms? So I think I'll be a little contrarian. I'll say maybe yes, relative to the baseline of the other responses. Clearly, there's interesting details to work out, but maybe I'm a little bit more optimistic that we actually do have some methods that have nice properties, and those properties, the differences between them become less prevalent at scale. That's roughly this kind of hypothesis I've been arguing for, that at scale, when models go to the infinite limit of parameters, data, whatever, they become more alike. And as we approach that asymptote, then maybe these differences between the different methods actually become less important. One thing I'm kind of interested, actually the architecture I'm most excited about right now is our autoencoders, vanilla autoencoders. I would love to show that those actually at scale can work with. You have to get the recipe right. Like, you always have to have some regularization. You always have to have some properties of the data. You can't completely ignore all design principles. But I think it's only a few properties you need. So I'm betting on autoencoders. We'll see what happens. But I do think that even though I think the algorithms might be there in an okay form, there's still more to do, but they might be in an okay form. I think everything around the algorithm, the data distribution that you train on, how do you collect the data as an agent as opposed to being given the internet, I think that's an open, important question. Maybe in the agentic setting, the types of representations that we need are going to be fairly different than the ones that worked well in the more recognition and passive understanding setting. But yeah, I'm just not quite so convinced that we're missing something fundamental in our architectures or algorithms.
Okay, I guess I have to say the opposite of Philip. I think I'm struck by how difficult it is to choose an objective function. And I'm struck, I've always been struck by that since I was a graduate student. I remember thinking, oh, I know how to, I have to solve I don't remember what I was trying to solve, trying to estimate something. And I thought, this is straightforward. I know exactly what I want. I just have to write down an expression for that. And then I'll just run gradient descent and I'll be done. 3 months later, I was pulling my hair out and screaming and pissed off because it was a much harder problem than I imagined. And I had stuck in a whole bunch of regularizers, and I had modified the objective, and I had reparameterized everything. And I had gone through, I don't know how many steps of trying to get this thing to work, and it was still a mess. And I had a sort of solution that I didn't quite trust, but I gave up because I felt like I'm done with this. I can't keep wrestling with this. So that was mid-stage graduate student, discovering how hard optimization can be. And it was really mostly because I didn't know how to write the objective function in a clear and in a way that didn't have unintended consequences. I was struck by Jan's talk that, all of the things that he went through and described, there are variations on objective function and formulation, and they all have these pitfalls. They get stuck somewhere, and you can try to get out of that by putting something into the architecture or adding a regularizer. And often you still end up kind of hitting a dead end or not quite getting the performance you expected. And I guess it makes me feel like we still don't really know the right objective function. One other comment, so biology is going to tell us a lot as we continue down that path about architectures. Finally, we're in a stage in neuroscience where people are doing circuit busting. We've got optogenetics and other kinds of tools where we can take small circuits in the cortex and figure out what each of those individual neurons is doing in those circuits dynamically. We never were able to do that. When I was a graduate student, I used to dream I wanted to work on cortical circuits because I thought, well, we're going to, once we figure out how that works, we'll understand everything. Well, that was a long time ago. And we still don't know the answer to those questions because it's been incredibly difficult to break those circuits apart and understand the dynamics and the behavior inside of those circuits. But that's coming, and it's coming pretty soon because of the technologies for making the measurements and manipulating and actually poking cells in those circuits and causing them to fire or be silent. So when I think that those architectures, that's going to change a lot in the way we think about architectures. I think that's going to give us more efficient architectures for learning and for representation. And I think, data sets, well, we just keep scaling up the data sets because we just keep gathering more and better data. So that'll take care of itself. So that's why I tend to think it's the objective function that we still don't know what to do. And biology can't really tell us that, other than just, what evolution tells us, which is that we evolved to survive and reproduce. That's not much of an objective function. So we're going to have to, I think, still wrestle with how do you get the objective function for the brain.
All right. So I want to make another observation about biology. So when we think about scaling data and adding more and more phenomena and types of images to our training sets, in humans, this happens linearly, right? You learn a lot about the world, and then when you're 15, you start playing the guitar, and now you have a whole new set of features that you're trying to learn, and the brain has to solve the lifelong learning problem, which I would say personally we're not doing that great at. So for anybody who doesn't work on this, the lifelong learning problem is basically learn 100 classes, throw away the training data. Now you're given a new 100 classes, and you want to change your network to learn about the new classes without destroying the old ones. People do this on a regular basis. They're constantly learning new phenomena without destroying the old one. And as it turns out, even though we can't trace individual neuronal circuits, I was in the neurosurgery business from 1989 to 1995, and we poked a lot of brains with live conscious patients, and you can tell what their cortex is doing in that particular spot. And through experiments like this on real people with real electrodes, you can discover that basically when you learn a new skill, it pushes aside the anatomy of everything else without really disturbing it much, and creates a space for new learning. And this is really different than what we do in lifelong learning, where every weight affects every class. So if every weight in your network affects every class, and then you introduce new classes, you have a very hard time learning those new classes without screwing up your old weights. The brain doesn't do it that way. It creates a new space and reduces the space. I love your skepticism, man. It's like intense. So this is what happens in the brain if you believe me from my OR experience. So I just think it's really interesting to look at how the brain solves the lifelong learning problem. It solved it spectacularly well. We don't know how to solve it yet with our models. So that might suggest changes, in particular, the locality of deeper functionality. So shared mid-range functionality like V1, V2, V3, and then isolated V4, V5, V6.
Cephalopods have a completely different strategy than primates, by the way. They apparently add new neurons constantly throughout their lifetime. The brain grows really rapidly all the way through the lifetime of the animal. I don't know how that works, but imagine building a network where you have to add new neurons every day and figure out how to get them to play nice with the old neurons.
Isn't it exactly what's that? Isn't it exactly?
Well, I think that's an interesting point that species like octopus obviously grow a lot of neurons. I mean, they start being about this big, and then they can get that big if it's the giant Pacific octopus. But they only live 2 years, and they get super smart in 2 years without ever meeting their parents because their parents died before they're born. It's amazing.
Yeah, if you have any questions, feel free to interject. Otherwise, okay, we'll just throw a last one.
I have a question. So, Iro, you talked about these circuit busting studies. This takes forever. It takes huge labs, tons of money. It's so much easier to just like mess with a deep neural network. So it really raises this question of if we truly who will get there first? Who will get there first? Yeah, I would bet on I would bet on Meta versus like us.
Okay.
Yeah, I mean, you really think
how much are you willing to bet?
Well, I like this a lot.
Let's get your wallet out, man.
Yeah. Okay, we can talk about that after. No, but I mean, and you're also taking it a step further. You find that circuit, and you're talking about a rate, maybe a rate code, maybe there's some molecular code, maybe some code.
Spiking code.
Spiking code.
Neurons.
Okay, yeah. You just need to translate that into some insight that you could embed into a deep neural network. And I've done that stuff that's like my whole career, just trying to do that, and it works to an extent. But then the ceiling that we've reached so far with those biologically inspired approaches, it's beat by an autoencoder with a lot more compute behind it. So I'm curious if you think we need a different computing paradigm in order to translate circuits to better models, or it doesn't feel like it's just going to be that next neuroscientific insight. It's going to be that maybe plus a lot other stuff. Do you have other ideas?
I mean, we've gotten a lot from neuroscience already, and the question is, of the stuff that's there that makes the brain function, how much of it is really important? There may be 3 levels to think about. How much of it is important in an abstract sense, computationally? And maybe your argument would be we've already gotten all of that out of there. There's nothing else to get. Then there's how much is important in terms of making the thing function, let's say, on low power and with noisy elements and with all of the things that come along with biological tissue, and also having to do online localized learning, because you can't do global propagation of gradients. It has to be something local. So those questions, I think we really have no idea how to do those things on the technology side, at least as far as I know. So I think that's an interesting mid-level of question. And then there's biological details that are about just keeping the thing alive and dealing with cell maintenance and stuff. And those presumably we don't need to worry about and shouldn't be worrying about. We don't actually know how to draw those lines cleanly between those 3 things. So I think, it's still a bit of a mystery exactly which things matter and which things don't.
Cool, thanks.
all clear day. I think a lot of the talks were talking about scaling up data, discovering principles for self-supervised learning. I was expecting to see some attempts at reducing the size of these networks, making them cheaper. I appreciate the fact that we are learning priors. So strictly speaking, we did not do it cheaply. But where do you see in situ learning, SSL learning going? Are we going to ever do it? Surely, biological organisms, whatever prior they are born with, they do seem to learn in this fashion on device. So.
I mean, I think in the end, we're going to need size. You know, I mean, those networks seem to get better the bigger you make them. So I don't think we're going to be able to kind of cut corners. On the other hand, there are two arguments about size. I mean, I think there is a good argument, which is the type that, you know, that's in the paper that Nicolas talked about, where, you know, you scale up self-supervised learning with bigger models and more data, and it works better, and you end up surpassing performance of even supervised systems. So, which even for situations like images for which we have like ridiculous amounts of labeled data, right? So that's really really important. Now there's another type of scaling, which is the type of scaling people use for LLMs, where you know, basically LLMs are used as kind of compressed information storage and retrieval, which is a point that Yi actually made in his talk, that you know, retrieval of information is not actually intelligence and ability to reason. And for that, obviously, you need scale because you just need a lot of storage capacity. Ultimately, the big question is related to what I made in my talk, that the amount of data that we train LLMs on is much bigger than the amount of data that humans are trained on, right? I mean, why? And that includes, it's not just true for language, it's true, you know, a lot of cultures, for example, don't speak to their children very well. The kids are not exposed to a huge amount of language, yet they learn to speak like everyone. It's the so-called paucity of stimulus. I think that linguists have been kind of arguing, I've been using to argue against the fact that language is learned, you know, the Chomskyists, the nativists in language. But also, like, in terms of visual information. So I made the point that, you know, a 4-year-old has seen a huge amount of information visually, but it's still not like a huge amount of information. We get really smart really quick, despite the fact that we have enormous brains. So what's the story?
Maybe following that point, because as you said, if you look at the whole quantity of data that a child has versus what we feed to a deep net, it may be different. But the way the child collects the data, as we saw in one of the videos with the eye tracking, is very active. And so in a sense, so depending on the age, I don't know exactly, but the quality of the data they get is really, I don't know exactly what's behind, so I'm going to turn a couple of things and figure that out. And so do you think this is what is currently the main maybe bottleneck, or what we need now in SSL, a better way to generate or curate?
No, I don't think it's a bottleneck because, I mean, developmental psychologists have studied this. So Linda Smith, who gave a invited talk at, was that NeurIPS or actually last time? NeurIPS, you know, has studied this, like, you know, how much learning takes place just by observation. So first 3 months of 3-4 months of life, you know, babies can hardly influence the rest of the world. They can move their limbs, they can, you know, suck their thumb and stuff like that, but they can't really grab objects. They can't like influence the rest of the world. Yet they learn a huge amount of stuff just from observation. Then you have, you know, you can start to grab objects and stuff like that. And then by the age of 7-8 months, they start actually making systematic experiments. So, of course, there is some active perception before because you can move your eyes, right? But then by the age of 7 months or so, they start doing like systematic learning. So if you put a 8-month-old on a high chair and you put some toys on it, they systematically throw the toys on the floor and they watch, because they do the experiment to verify that gravity applies to everything, essentially. And then it's much more kind of exploratory. So all of play essentially is a way to like fine-tune your internal mental world model in situations that if you were to encounter them in reality, you wouldn't be able to apprehend because your world model hasn't been fine-tuned for them, and maybe it will kill you. So it's probably better to kind of handle this in a situation that's not dangerous beforehand. So yeah, I mean, it's a whole progression. But I think with SSL, we're not even past the first stage yet. Like, how do we get system to learn really well just by observation? And we've done also some experiments with like action condition world models here. But I think that comes afterwards. You need to have a good representation of the world that you've learned from observation, essentially before you can learn good action condition models and like figure out what an intervention in the world will result in.
I think one area of AI that was very popular a while back also with beta VAE was learning disentangled representation. And this hinges on the same idea that if you have a really nicely organized latent space, you can solve a lot of tasks in a very few shots, and you really keep all the information, you just reorganize it. So in theory, you can solve pretty much all the downstream tasks. And this thread seems to maybe not have died down, but at least it's not as popular in today's conferences. So what do you think?
I don't know.
As a place
no, I mean, I think it's, I mean, certainly criteria like VicReg, MCR squared, MCR, etc. They try to decorrelate variables and in a way, or make them independent if you use tricks, but in a way that that is a way of disentangling variables in the representation. So parameterizing the manifold, if you want, the data manifold into sort of independent explanatory factors. So I don't think it's out of the picture. Maybe the word is not being kind of said explicitly anymore, but I think you get this as a side effect. One type of work also that I've been involved in is kind of separating the invariant from equivariant part of the representation. So there are criteria like slow feature analysis and sort of invariant representation learning, where you take successive frames, for example, in a video, and you tell the system, well, it's really the same content in those 2 frames, so you should have a criterion that makes the representation more or less the same. Now that of course causes immediate collapse unless you have something to prevent collapse. But even if you have something like VicReg that prevents collapse, you still we did this experiment where you have a very, very simple video, basically uniform background, and you have a single dot moving on it, and you train a JEPA using VicReg to learn a representation of it, and then you measure to what extent the system has the location of that moving dot embedded in the representation. So if it's a uniform background, the dot is there. You can train ahead to predict the position of the dot, and it works. If you put a noise, background noise, and you change it at every frame, the system learns to eliminate that noise and basically pick up the dot. So it still works. Now, if you put a fixed background noise or a structured image, then it stops working. The system basically doesn't pay attention to the moving dot because it's just a few pixels, and basically uses all of its bandwidth to encode the background image, and that takes over. And so if you want the system to pay attention to the moving dot, you have to have an extra criterion that says, make sure that successive representations are different. So it's like a contrastive term that you add to it. And there it works again. It pays attention to the dot, but you could apply those criteria differentially to different parts of the representation so that one part is invariant and the other part is equivariant. So it changes with time, and the first part doesn't change too much with time, it's more invariant.
Onto that, because the way biology works is for a lot of the variations that we want to be so-called invariant to, biology takes care of it for us by, say, tracking an object. You just, when you're interested in something, you track it, you stabilize it, and now you don't need any of these things. So here's a question I want to pose to all of you. Like, we all love, say, translational invariance in our object recognizers. Now, why do you think that we saccade to a particular part on a face or track things when we could do it all in software? I could just stare straight ahead and watch a video and have it learn an invariant representation that doesn't matter where the thing is in the image, or I could evolve an incredibly complex eyeball system with 3 sets of muscles to track the object so that it's stable. Which one's easier? Now, most computer vision people think it's easy to learn translation invariance in software. It's not. It's super hard. It's so hard that biology has created eyeballs that track things. And not only do we track them, how many of you know that we track things as they rotate also? You have oblique muscles in your eyeball that if I turn my face like this and you focus on my face, your eyeball rotates to track it. You don't learn invariance in your brain, you track things. And, you know, how do you deal with brightness invariance? Your pupil contracts to renormalize the image. You don't learn that in your neurons. So all these things we love to do to train software to be invariant to stuff, biology is handling in a completely different way.
I can disagree with this a little bit.
There are lots of animals that don't move their eyes.
So which part? No, I mean, the reason, I mean, obviously biology doesn't have shared weights. So the trick of like having a system that can recognize, you know, object anywhere in the visual field doesn't work. But there is another argument, which is that, I mean, we have foveated vision. We have much higher resolution in the fovea than in the rest. In fact, you know, Aero has studied this a lot. And the reason for this is just, you know, hardware minimization. Like if you want high acuity, accurate vision, you can't afford to have the hardware to do this with a wide field. You have foveated vision and you can move your eyes. Now, here's an interesting thing though. Rabbits don't have a fovea like ours. Their fovea is horizontal and covers the entire visual field. Why do you think that is? And it's shift invariant to some extent. And the reason is, right, as soon as they see a predator anywhere in the visual field, they have to run.
No matter what they see. I mean, they are incredibly stupid. If they see something move, then they run. And that's basically how they work.
Yeah, I actually believe that, see, the nature is very smart, right? See, they probably don't just solve one problem with purely hardware solution or purely software solution. There probably is a little bit balanced. For example, there's the variance can be solved by certain arrangement of your, you know, your neurons. But also the part of the tracking is also important to make it more precise or for other purposes. For predators, for example, it's important to have. And just like us, right? For example, I study multiple geometry. And in theory, I mean, you can recover 3D environment, including also even, you know, dynamic environment with a molecular camera, right? Molecular videos, in theory, mathematically. But it's a much harder problem, right? The motions and the 3D structures are compounded. If you change your camera view, the motion, also the things are dynamic. It's not impossible mathematically, but it's much harder problem, inverse problem, yield condition and so on in many cases. But then we have 2 eyes. Then we take a snapshot of 3D and separated the time and space a little bit. Not entirely, but still things still come. But the solution, then you suddenly have a probably much easier optimization problem to do the reconstruction to recover to learn the distribution of the 3D plus time dimension. So hence to me, this is a perfect, right? A sort of combination of hardware and the software problem. Then we have 2 brains to solve the stereo problem, which is much easier than we have 1 eye. We have to sort out the 3D by moving around, as well as tracking the dynamical or limbs of multiple moving objects. So I think the solution is really, I think it's in some way it's an optimization problem, but it's a mix of hardware and software. Right? It's all part of that solution, which minimize the sort of resource or energy or something, right? Give you the most efficient solutions. I think nature is sort of doing that. I think our current system is a little bit extreme, which has solved all things by just hardware or data model. And we were joking, right, during the lunch, right? So in order to realize the ReLU function, we go through millions of transistors and compilers, GPUs, and PyTorch. We write a ReLU. In physics, you can realize that with the one single diode, right? And this is the kind of things we're dealing with, right?
And to simulate one biological neuron, you probably need, a couple thousand ReLUs. So, and each of those needs many millions of transistors. So, wow, it's really incredibly inefficient what we're doing.
One just thought that was provoked by this. I wonder if we can see this as Barlow maybe did. Is it redundancy exploitation? So we have two eyes and they can serve as a supervisory signal for monocular depth. And maybe we have saccades that can serve as like a supervisory signal for translation invariance. Yeah, maybe there's a connection to that.
Well, see that, yeah, just to add to that. So I think, maybe we have two eyes, really we can train our right eyes with our left eyes. And I find it's also self-supervised training, right? We can use in reality, in theory, yes, we can. If I have single eyes, I can probably predict the depth, but I can use my left hand to correct if my estimation is accurate or not, right? This is kind of we set up, even our sensors are set up in such a, allows us to do self-supervision, right? That's actually kind of amazing, right? At least to me.
Yeah, you asked earlier, will scale get us there? And I think at the end of this day, I really enjoyed all of the talks and all the lightning talks. I'm still unclear on how we will know when we are there and what there will look like. What are we expecting to see? We talk about models that can learn as sample efficiently as babies, but babies aren't very good at many things. So like, what is it that we're expecting to see once we're there? And what is the thing that we're trying to solve?
Well, for now, I think I'm interested just can we get the data distribution learned correctly or efficiently? That we're at that stage. But as I asked in the end of my talk, right? I don't have answers that even if we have a system claims to have certain ability, even memory, can we check if it really has learned that distribution correctly, or even learn the distribution, memorize something, or is that really means understanding? That we understand natural numbers, but can you verify any of the large models? And what is the sequence of tests? Right? What's a procedure even, implementable one? And so that the conclusion is scientifically meaningful, convincing, or even statistically, with certain significance, right? Even as a hypothesis, the system understand natural number or not? What's the p-value? Give some, a confidence level. I mean, is there a procedure to reach that conclusion scientifically? Well, I don't even know that. So I think there's a lot of, even questions about, about the Turing test or, Wiener test or even, so we need to define those things now. What are the tasks? What are our capability we're testing? And then investigate how do we test it? Rather than just, there's some doing great on benchmarks, right?
Well, that's a serious question for a lot of stuff that we're doing. Been asking ourselves that question a lot, right? So how can you figure out that you've learned a good representation? So, I mean, the obvious procedure that people have used in SSL for a while is you use the representation, you freeze the encoder, and you use the representation as input to a downstream task that you train supervised or something. The stuff we become more interested in recently is you use the representation to build predictive models that are action conditioned, and then you see if those models can be used for planning a task. But then there is a lot of moving parts. There is like which cost function you use for deciding whether your task has been accomplished. I mean, there is a lot more. It's a lot more difficult to like figure out if it's just a representation. But what you have to do is use a wide diversity of tasks. People testing LLMs has a similar problem that if you have one benchmark, people can only study for the test and then get good results on those benchmarks with specialized systems that don't actually work on others. And so it's there's a similar question. People have been trying to come up with like those tests that are supposed to test for AGI, whatever that means, whatever you mean by this, right? There cannot be any single test that tests for AGI or human level AI because the type of intelligence that we observe in humans and animals is not a collection of skills, but it's an ability to learn new skills extremely quickly, or even solve new problems you've never been confronted before, zero shot. And so those are the kind of tests that need to be done. And the protocol for this are not trivial. As the system becomes smarter and smarter, the protocol that we have to put together are going to look more and more like what psychologists use to test humans. And we know how reliable this is. I mean, it's a big problem.
Just to add a little bit to that, like one thing that is discussed a lot these days is the fact that a lot of these advanced models are not very well calibrated. They don't necessarily know. They're not good at evaluating their own confidence or realizing when they're incorrect. So in our lab, one of the things that we're trying to understand better is how do you build a system which will naturally respond, I don't know, when the probability is low. Now there's a million ideas around this, right? Well, we just need, we need to use Gaussian processes and make everything a posterior. And a lot of those things don't work very well yet. And one of the properties, I used to work in a neuropsychology lab, and we would do scalp electro recordings from the scalp, and you can give somebody a prompt like, do you like your coffee with cream and dog? And when I say the word dog, you get a big voltage potential across your scalp because you don't expect it. And whenever you're surprised as a human being, you're presume, part of your cortex kicks in and tries to understand what about its model, was not predicting the future correctly. But that, if you think about it, that requires making almost constant predictions about everything happening in the world around you. And it's only when those predictions are expected to be correct and they're not correct that you try to learn. So I guess what I'm saying is, I think one of the biggest differences between current advanced models and humans is that humans seem to be constantly making predictions and rarely surprised, but what they can be surprised in 1,000 different ways at any moment. That's so different than these big models, which are focused on one task and one posterior with very little context. So I think closing that gap is a big part of moving forward.
So we are unfortunately at time, and because it's 6, I don't want to keep people, but maybe one very last thing. So if every one of you could just in one sentence give an advice to a new graduate student who wants to get into SSL research, what would it be? And yeah, just one sentence, and it has to be something you did not say in your slides already. So.
I mean, you just have to have fun doing it, I guess, and be passionate about it, and it should be easy and enjoyable.
Well, I had a whole slide with a bunch of recommendations, so I don't need to repeat those. But like, be ambitious. I mean, what we're after really is building intelligent machines. So that should be the long-term goal, and then kind of work your way back. Like, what's the first step you can take?
Yeah, I follow up Yang just said, right? So that I think the goal for building truly intelligent system is not there yet, right? Has not been achieved. I mean, this really makes this probably the most exciting time for the younger generations. We barely scratch the surface, and what has been done so far is pretty primitive. And there's just great problems now, how to really understand intelligence, both scientifically and also even to me, mathematically and computationally. And we're at the beginning of that. I think that's really very exciting. Actually, it's really more exciting for academia than industry, I think. Yeah, make that your, yeah, that's my.
Mine would be to learn vision with a capital V before doing machine learning and deep learning.
I guess mine will be to be contrarian, find the thing that everyone believes that is wrong. And I think that comes across in a lot of the talks the folks here have given. I'm trying to imitate that a little bit, but I think Jan and E and others have done a much better job at being correct and contrarian.
So I have to say, find the thing that everybody believes is right and show that it's wrong. Just because I have to be contrarian with Philip. No, I guess I would say I dream of a more sort of scientific approach to machine learning in general, focusing on this is an amazing time that for all of you young people growing up in this. This is just unprecedented and absolutely amazing, but it also feels incredibly chaotic and confusing. And I guess for me, the idea of a little more focus on fundamentals and understanding, a little bit less on benchmarks and tables of numbers. Sorry if I'm offending anyone, but just my preference.
I'd say look at the biggest differences between how humans do things and how these models do them, because the reason they're doing it differently is likely to be interesting.
Thanks. So let's thank the panelists one more time. And so, yeah, this concludes the workshop, and hopefully there will be another version next year. And I will make sure to send an email to everyone. And meanwhile, have a great evening, and thanks for participating.